Alright, so next up is problem number 31. So 31 asks, a car is traveling on a level road. Okay, level road, car. Boop-a-doop-a-doo. Okay, we'll make it a sporty car, give it a spoiler, and a hood scoop, and some flames on the side, because we do cool things here. And we'll give it some windows because, you know, cars have windows. And it has a windshield too. And then it has doors and a handle and really cool rims. Just give them black rims because black rims are cool. They don't have round tires though, because they're too cool for round tires. Anyway, so it's moving with a velocity of v0. That is a terrible v, but hopefully you can kind of tell that it's a v. So it's moving with a velocity of v0. Sorry for the glare. And at the instant when the brakes lock, so the wheels stop turning, completely locks up, and then we want to use the work energy theorem to calculate the minimum stopping distance of the car in terms of v0, g, and the coefficient of friction, which is mu k, and I think that is it. So yeah. Okay, so the minimum stopping distance, the way to figure this one out, is this the right one? This is the right one. Okay. So you're going to use your momentum and energy equations. So you're going to get the kinetic energy beforehand, so K0 is equal to your kinetic energy after, plus your friction, or the energy from the friction. So kinetic energy is given by 1/2 mv, so this is v0 squared, and that is going to be equal to stuff that I'm going to put over here, so it's all in one line and looks nice. 1/2 mv squared, so not v0, plus, and then your equation for kinetic friction is, what is it? It's mu k times your force, your normal force, times your distance traveled, if I'm right. And then it wants us to solve for the distance traveled, so we're solving for this guy over here, which means we need to move everything else over here. The first thing I'm going to do though is I'm going to break the normal force into gravity times the mass. And then we have mass everywhere on that, so we can just completely remove that from the equation, just divide it out. And then, yeah, I think we're good to go. So, I'm going to subtract 1/2 v from this side, so you get 1/2, and then I'm going to just bring it out as well, because both of these have it. So this would be 1/2 v0 minus 1/2 v, and those are both squared. So I just brought the v out, so it's a little cleaner. And then that's going to be equal to mu k, or mu sub k, times gravity times x, and then you just divide everything by mu k gravity times gravity, and then these will all cancel out, and you'll be left with x is equal to 1/2 v0 squared minus v squared over mu sub k times g. And if you want, you can make it look a little prettier by taking the 1/2 off and just putting a 2 down here. So that is part A. Boom. Oh wait, the x is kind of important in this, isn't it? I'll just add it in real quick. Okay. And then for part B, it asks us, by what factor would the minimum stopping distance change if I, or 1, the coefficient of kinetic friction were doubled? So if you doubled this, you would essentially be changing this to v0 squared minus v squared over 2 times 2 mu k g. And then if you look at that, like, it's pretty easy to tell you're adding an extra, basically 1/2 to the bottom there. So this is going to decrease, let's see, make sure I get this right. The minimum stopping distance would split in half. So the distance x would be cut in half, because you're basically, like, if you take this out, you can actually, like, factor this guy out so it's over here. So that's going to be a factor of 1/2 that you can bring out to get this to look the same. Once you change the coefficient of friction, you double that. So that's a factor of 1/2. Or the stopping distance, yeah. Okay, so for the next question, so this is, it would half it. So then the second part, so part I, because they use stupid things instead of just A, B, C, D, they ask if the initial speed were doubled. So in this one, we're going to go ahead and put in 2. That was a terrible 2. Hang on a moment. So if you doubled V naught, so in this you'd have 2 times V naught, and then that's squared. So in order to pull the 2 out front, so we can figure out what coefficient or what factor this changes it on to reset it back to this equation here. If you squared this part, let me just write it over here. So if you have 2 V naught, and that's all squared, that's equal to 4 times V naught. And you can do this if you write it out. So if you were to take off the squared here and just write it to 2 V naught, and you just multiply, that's what you get. So this is equal to 4 times V naught squared. And then since this is a number on the top, you could actually just bring this straight out as well. So this is 4 over 1, I guess, which is still just 4. So the answer to that one is it would multiply it by 4. So if you had to double, the starting velocity or distance would be 4 times as long to get to a complete stop. So then for I, it asks what would happen if both the coefficient of friction and the initial speed were doubled. So we could go ahead and plug this back into our equation here, or we can just look at this and multiply those two together, and that gets 2, and that's the answer.